We were talking about the rubidium strontium system, and also we just looked at the rubidium strontium isochron from meteorites, right? Remember, these are the meteorites we consider as the A chondrites. I'm not going to teach you about the chondrites now, but you can refer the literature and find out what are the differences in chondrites. Okay, there are different types of chondrites. That means the initial building blocks of the planetary system. Achondrites, chondrites, iron is different types. There are several types, but we are not here for discussion on that anyway. But those who are interested, I think it's worthwhile looking at the textbook of Isotope Geology. It will show you in the initial chapters. Okay, as we know, the strontium system, not only strontium but other systems also, we can use just more than a tool for age dating, right? So that means regarding the evolution of a system, geodynamic system or a rock system, we can use these isotopic systematics. So that's important. We will look into such examples later on. But I just want to remind you about this isochron. So isochron means equal age line. Actually, the meaning of isochron, iso means equal, chron means something related with time, right? So if we have similar isotopic compositions at the very beginning, that means a cogenetic system, right? So all the chondrites are supposed to be derived from one material, everything derived from the same materials for planetary formation. So therefore, we can analyze multiple chondrites or meteorites, and then we can plot them and check whether they have they show any collinear pattern, right? That means isochron, right? Present day we can see the isotopic compositions and see. In case if they are moving away from the most common isochron, for example, here there is one point that is away from the line, right? But it's very close. It's we can get it, but I mean, likewise, there can be some deviations, right? So some points might be here or here, like that, right? In that case, we can't take such points for the isochron because the slope is very crucial for an isochron. If you change this slope, that means this angle theta. If we change, that changes the date, age also, right? Because E lambda t, it's E lambda t. So when you derive t from E lambda t, it's the effect is very high because it's a natural logarithm is involved there, right? So therefore, you have to be very precise on this slope. Otherwise, you don't get the correct age. And also, this plus or minus value, okay, this plus or minus value is also important. This is what we call uncertainty. Okay, uncertainty means error, right? There can be error, right? If you say your age is say 23, then you are not precise enough, right? It can be 23 years plus plus or minus 2 months or something, right? One can guess that you are 23, but someone can say no, he or she is not 23, more than 23. So that is based on the error, right? Uncertainty. Unless otherwise you give the precise age or precise value there. This is common in any analytical protocol. So you always have this plus or minus value, right? So this is derived by MSWD. You know MSWD? MSWD, mean standard deviation, mean standard weighted deviation. Okay, in statistics, you can learn that MSWD, MSWD, right? So this is associated with regression. Regression means I think you know it already, right? Regression. So when you have some points, right? Some points may be like that, some distribution of points. You select the best fit line, right? Best fit line means you can have different lines like these three, or this way, this way, like that. You can have different lines, right? Depending on the number of points, and also uh, number of the deviations or whatever. Okay, but when you do this regression analysis, you can use this MSWD to minimize. If you get a very minimal MSWD, that means you are getting a best fit line, the most suitable line. That is the more reasonable, statistically reasonable line. Okay, so likewise, this isochrone line is also a best fit line, right? A best fit line that will give you an age, right? But some isochrones, when you do this regression analysis, if it is really not the best fit line, or otherwise, if your analysis is biased in some way, for example, you are getting some isotopic values more, I mean, more more numbers towards this side, right? But you don't know whether this is really the situation or not. It might be some analytical problem. Okay, there may be some analytical problem. For example, sample preparation for this isotopic analysis is very important. And if any contamination is there, there will be deviations for isotope for the values that you are getting, maybe this way or other way, right? If you are supposed to get a line like this. Okay, so therefore we have to be very careful on sample preparation also, right? Human errors and also some analytical errors can cause this type of problem. So in that case, uh, uh, you will not, even though you get a very good MSWD, because you have nice points here, so you will get a line, and also you will get a very minimum error, the standard deviation. This is a type of standard deviation. Okay, uh, but still it is not your age, correct age, right? Because of some kind of bias, right? So these are analytical problems that you have to keep in mind. You can learn much on these if you go for your isotopic studies in the research stage, in your after graduation, masters or PhD or whatever, right? But anyway, uh, if the system is not closed for the rocks that you are considering, can also give you some erroneous isochrones, and also they can give you some very high MSWD also, right? For example, if you are analyzing non-cogenetic rocks, and you are supposed to get a high scatter. Okay, so if you are getting high scatter, you cannot have a good isochrone line, right? That means you cannot have a good regression line, because the deviation is very large, very high, so that the statistics cannot compute a very minimal MSWD for you in such cases. Okay, so always MSWD will be very large, sometimes 40, 50, 100, something like that, right? But if you are getting MSWD like point something, like here, right? Point 0.02 here in this case, right? Or 1 or 2 3 4, like that, maybe okay. But if you are uh, getting a large value, that will be a problem. But remember, that also depends on your age also, right? For example, here 4.39 billion years. Okay, it's billion years, 4.39 billion years. and you are getting an error or uncertainty of 0.26. 0.26. Sorry, I think I don't know whether you got confused. This is not the MSWT. Okay, this is the uncertainty of your age. MSWT value should be given separately. Okay, if it is a point some 0.1, 2, 3 or something like that, that will be very good. Okay, remember MSWT is given separately with your age, right? So that determines how large your error is also. Okay, that's the point here. So if you are getting large MSWT, that means you will be definitely getting a large error also. If you are getting a low MSWT, you may get a low uncertainty, right? So if you are getting large uncertainty and a large error, right? For example, in this case, 4.39 billion years, and the uncertainty is 0.26 billion years. Okay, so it's very good result. Why? Because 4 billion years means very large number, right? Billion years, 4 billion years, and 2.26 billion years means very small number, right? Because we are talking about billion years, right? So therefore, this is a very good value. But if you are getting here some uncertainty like plus or minus 1, that is also very large. Why? Still it is in billion years, right? So if you are telling that your rock is as old as 4 billion year plus or minus 1, that means your rock can be even 5 billion year or 3 billion, right? 1,000 million years difference is there, right? So that is very large. So therefore, you cannot accept this type of uh, errors uh, in isotopic analysis, right? But suppose you are analyzing a metamorphic rock, which is supposed to give you some age like 550. Okay, so 550 plus or minus, you will be getting some value like say 20 plus or minus 20, right? This is okay. This is acceptable. Why? Your age can be 570 or 530. That's okay, right? Just 20 million year difference is there. But if you are getting something like 120, then that will be a big error, right? Because your age can be 670 or 320 or something, right? 420, 420, yeah? 420 or something, 430, right? Plus or minus. Because there is a large difference, more than 100 million. So always think about this decimal point, sorry, this digit. If you are getting the error also in the same, the largest digit you have, that means here 5, here 1, the same position, then it's a problem. Okay, but if you are getting something lesser than that, it will be okay, right? Even I mean 90, if you are getting 90, 80 like thing, error is large, but still you may be able to accept it, right? It depends on your interpretation anyway, right? But still we prefer if you are getting some error like less than 50, that will be very good. Okay, so like that, this error is determined by the standard deviations. Okay, so this error is determined by standard deviations. So especially when you give isotopic age results, it is better if you are giving the MSWT value also, right? But in this case it is not given, only the error is given. But it's better MSWT is also given, so that the person who reads it, or the audience, will be very clear that your population is statistically reasonable. Okay, so that means you can accept the data as good data because you are presenting a very fair age population, right? So that thing is there, which is common for any age dating technique. Okay, uncertainty. Right. So in this case, from meteorites, we get this type of an age. So you can see it is very consistent with our age of the Earth, 4.56 billion years. So it's a very nice isochrone, right? So this means no disturbance, exterior or exchange disturbance. So that means this has kept closed system behavior, right? That is one of the main assumptions we have in isotope geology. But in case if you have an open system, then you can't apply this isotopic systematics. But you can still apply uh, even for open systems just to tracking the processes, okay, whether the rock or the magma has interacted with the hydrothermal fluids or some other mixing processes like magma mixing, because there can be several batches of magma mixing later on, because one magma can be produced and which is going up to the shallow levels, maybe it's very slowly, right? But the second batch of magma from somewhere else within the mantle can come up fast and mix with the previous magma batch, right? And then erupt as a single magma eruption from a volcano, right? So the rocks that you find there on the surface will have a mixed magmatic properties. So you can apply these isotopic systematics and resolve what kind of two magmas were involved in this rock generation just by looking at the isotopic systematics, right? So in that case, we are using as a tracer, right? Tracer as a tracer, tracer, tracer. That means kind of an indicator to find out the previous history. Okay, right. And the other thing we discussed was the strontium ratios that we can find in the present day rocks. Here, you can see the present day rocks. Mob is having this type of value. Just keep in mind, if you can remember these numbers, that will be very good. But I don't want you to keep them in your mind, but it's always good if you can remember, because you will have a very good knowledge in that case, just to compare when you get a value from this isotopic system. For example, if you analyze one of your samples and just if you want to compare that with these standard values, that will be very good. Okay, at least try to keep in mind this up to this point even, right? Continents have greater than 0.7, Mob is almost zero point 0.7, and ocean islands also give you zero point 0.7, but it might be lower than that value, because as I said, uh, they are mostly unfractionated, right? Because the ocean islands are produced from plume magma, which is coming from lower mantle region, right? Even very below part of the lower mantle. So we believe lower mantle is still unfractionated and maybe similar to this chondritic composition. Okay, uh, that's why you are getting ocean islands like Hawaii, low isotopic values compared to other reservoirs. We call this as reservoirs. Okay, and meteorites, you see, the pure meteorites have much low isotopic values compared to our terrestrial rocks. The reason is somehow these are fractionated. Even I said ocean islands are coming from unfractionated lower mantle. It is not 100% unfractionated, and also during their ascent, they can be fractionated, right? They can be interacted with other things, and their low isotopic composition can be increased like this. Okay, if any pristine lower mantle sample you can find, most probably you will get a very low value, like very close to this number. Okay, that's the natural phenomenon. And we discussed again why all present day strontium isotopic ratios are greater than Barbie. The basaltic chondrite best initial, why they are greater than Barbie, because now we know our planet is differentiated, right? A lot of males have produced, and these males encompasses a lot of rubidium, and since a lot of rubidium is there for over a long period of time, there is possibility for accumulation of large amount of radiogenic strontium isotopic compositions. Okay, so if you have a lot of rubidium in the parent, that means if you put it once you put it for evolution for a number of years, that rubidium, that initial rubidium, will decay, producing strontium, right? So the higher the parent there, the higher the dot isotopes will be produced. That means strontium will be getting enriched. Strontium isotopes will be getting enriched in the long run of your samples. And why are the continental values are the highest? So that is the same reason. Continental crust is produced as a result of partial melting of the upper mantle, right? Upper mantle. During this melting process, rubidium is more incompatible compared to strontium. Therefore, a lot of rubidium from the source will go into the melt. That means that melt produced as the continental crust later on will accumulate a lot of strontium by radiogenic decay of those previously accumulated rubidium. Okay, so that's why the continental values will be showing the highest numbers. Okay, so any question? Do you have anything unclear? Because today we may go to another isotopic system. So if you are not clear something, we can discuss more. Okay, right. Then we'll move. We have another diagram to look at. Uh, I think you can remember we discussed the initial isotopic composition is equal to the value given by this Barbie, right? At the beginning, that means the time of formation of the Earth, right? 4.56 billion years ago. So what you can expect from this one? Earth should have been evolving like this, right? Along some decay scheme. Initially, they may have some value like here. Okay, initial composition of Barbie, right? Should be equal to this value. What is that value? What is this value? Here you have it. 0.699. That is the initial composition. Okay, so you have the 0.699 here. That is the initial composition of at the time of formation of our planets, right? It's the time of formation of our planet. Then this initial value, strontium value, uh, was there, and then the some amount of rubidium uh, parent uh, atoms were there, and they decayed gradually, so that uh, little by little radiogenic strontium was accumulating there. Okay, radiogenic strontium was accumulating. So with time, what happens? When it becomes younger, little by little, strontium is accumulating, right? More and more strontium is accumulated because of rubidium decay. Rubidium decays to strontium with time. So therefore, with time, strontium isotopic composition will get increased. So that's why you have a evolution in this way, like this. Okay, right. So at a time like 3 billion years time, right? 3 billion years ago, or 2.8 to 3 billion years time approximately, right? It's not exactly these three, but just close to 3 billion years, you can say. What happened? There was a large uh, differentiation, another differentiation occurred in the earth. What was that? Continental crustal formation, right? So how did this happen? Partial melting uh, started to appear within our planet Earth. So partial melting started means what? What has happened? Convection has started. Convective forces, convective cells in the mantle have started. Otherwise, you can't do melting, right? I mean, without any other heat source. If you want to do melting, either you have to increase the heat, or otherwise you have to decrease the pressure within the mantle. Okay. Decompression, right? So as soon as the convection started, convection it accompanies with material transport. Then from deeper sides of the mantle, material can come up to the shallow levels uh, and start melting, forming mid-ocean ridges and things. So that means uh, plate motion has started, right? So remember, until approximately 3 billion years time, there has been no plate tectonics. Plate tectonics, there may have been some kind of motion, but not like present day plate tectonics. So early plate tectonics started at about 3 billion years time, right? 2.7 to 3 billion years time. So that is the time when this mantle started to vigorously convect, right? So due to that, partial melting started, and that melt, uh, especially from very shallow regions of the mantle, that means the upper part of the mantle. So originally you had only one mantle, right? Mantle and core. But now, since this mantle convection started, the upper part of the mantle started to differentiate, forming partial melting. So one newly produced melt was separated. It was escaped from the system, so that the upper part of the mantle became depleted, because a lot of incompatible elements which love melts have passed with the melt. So the upper mantle started to become depleted. Composition become depleted. So now that is the time when this next step of differentiation started. So now what we have, the layers, the escaped melt formed the crust, continental crust, and then we have the upper mantle which is depleted, and then we have the lower mantle uh, portion plus the core, right? So this is the second stage of depletion. So here, uh, this depletion caused uh, the upper mantle to deplete. So here you have the depleted mantle, which is evolving in a different direction now, because previously they came in a direction like this, but now because of this differentiation, partial melting, the upper part of the mantle became further depleted, so that it reduced its strontium isotopes, because a lot of rubidium went with the melt, the continental crust producing melt. So the upper part of the mantle became depleted. So therefore, we call it depleted mantle, DM. Okay. So DM, depleted mantle, uh, was started to form, and the continental crust, the melt produced by this partial melting process, evolved in a separate way from there onwards. Why? A lot of rubidium went there, and a lot of strontium was produced with time. With time, a lot of strontium could be produced in the crustal melts. Okay, so depleted mantle evolved like this, but it was able to still produce some further melts from the depleted mantle portion. So it produced later on mid-ocean ridge basalts. So remember, mid-ocean ridge basalts are having almost equivalent composition to depleted mantle, because they are the products of depleted mantle. The early depleted mantle started to produce mid-ocean ridge basalts. Okay, so we call sometimes for depleted mantle as the source of mob, right? So therefore, some people call for depleted mantle DMM, right? People call it DMM also. Why? It says D means depleted, M means mob, and M, the second M is mantle. Depleted mob mantle. That means the source for the mob, the source area which produced mob, mid-ocean ridge basalts, DMM. So this composition, you have this upper mantle, the depleted upper mantle, DM, and DM produced mob. Okay, this DM produced mob. Since the DM, depleted mantle, is already depleted in incompatible elements, you don't see very high change of strontium isotopic composition in the mid-ocean ridge basalts in mob melt, because it's almost same as the DMM, depleted mantle, or DM, depleted mantle, because a lot of rubidium has already gone with this continental crustal production. Okay, so only very little rubidium was incorporated into this other partial melting process taking place at the mid-ocean ridges. Okay, so for MOB and DM, almost very close uh, uh, isotopic composition is there, because they were in equilibrium condition also. So they were remaining there as in equilibrium state, but this melt carries some of rubidium that can make a little enriched in mob melt. For example, like very slight change. If you want to draw, you can draw mob composition like this, right? Actually, you can draw the mob composition like that, and you can just cut this one and just put there DMM, DMO, DMM, right? So you can put the mob for this line. You can put mob, sorry, for this line. Okay, the second line that I drew, but it won't cut this ocean island line. Okay, it won't cut the ocean island line. That means it will evolve something like this, lower than that composition. Okay, this is the mob composition, actual mob composition, if you want to draw it precisely, right? So that is the mob, right? You can still take the black line as the depleted mantle evolution line, which you can show, oh, maybe like this. Okay, so below the mob line, slightly below the mob line, right? So now you should understand, if your mantle or your source evolved like that, any melt produced from that source can be represented in this way. Look. If you have a source mantle or source, any source composition, whatever, right, mantle or crust or whatever, but we consider it as a source, and this source produces a melt, right, at a certain period of time. So that melt can be represented uh, like this. That means definitely it will be little higher than the original source, because for the melt there is affinity of rubidium to go. So therefore uh, there will be some deviation. So original source can be uh, evolved continuously like that, but the melt produced out of that could be evolving in a other way, I mean a deviated way. Okay, right. So this is how the reservoirs in the earth evolve when these highly incompatible elements like rubidium goes into the melt. So this happens for highly incompatible elements. So remember, in the rubidium strontium system, rubidium is the parent, right? Strontium is the daughter, and if rubidium is more incompatible than strontium, therefore a lot of rubidium will pass to the melt when it is a product from the system. So in rubidium strontium isotopic system, this is the most important fact. Whatever the product from a melt will carry a high strontium isotopic signature. Okay, so if you measure it present day, then you will see very high value compared to its source. Okay, so why these ocean islands lie on this broken line? Ocean islands, why do they lie on this line, this broken line, which is the same as the Barbie? I said ocean islands are products of lower mantle, right? Lower mantle, we assume, and also not just assumption, evidence is also there to have almost equal composition to the primordial or meteoritic or chondritic composition. So therefore, uh, ocean islands should evolve along that line, right? They have not fractionated. But in case if any ocean island has interacted with a mob or some other continental crust or what some other source, then definitely they will deviate from this original line. Otherwise, very close to that line, they will reside. So you can see here 0.70 for ocean islands and meteorites 0.699, right? It's almost same. That's what we mentioned. Okay, so that is the reason why you have same line. So you can find several reservoirs in the earth now, right? What are the reservoirs? You can have this one, depleted mantle, right? Depleted mantle, and you can have mob, mid-ocean ridge basalts, and you can have ocean islands, right? That represents the lower mantle. This represents the lower mantle, LM, and we have chondrites still, right? Original composition, meteorites, right? If they are not affected by later processes, right? Like atmospheric burning or anything, if nothing has happened for the isotopic systematics, then it's very good. You go and look at the geology museum in our department. There is a description about a meteorite, right? Collected from maybe Kaluganga. right? There's a big poster prepared by LRK sir, so you can go and read it. There has been some analysis done on that also, so you can understand whether that meteorite is evolved or not. Okay, you just go and see. And by looking at that abstract, you get some point understanding, and make a small note in your own on your own. Okay, and submit it to the Google Classroom. Right, I will evaluate it, because as part of the continuous assessments, I want to give you some tasks like that, small tasks, right? But I want to know whether you understood or not about this evolution and all that, right? So you go to the Geology Museum when you have time, and make sure you submit it by next week before our class, right? And also there are, I think, some abstracts published in GSSL also. Maybe you can find them also. I can't remember whether it is Kaluganga or Kalugalatan, I think. Yeah, Kalugalatan meteorite, I think. Right. Yeah, you look at that and give a brief note on your own. Just less than one page. Okay. Then okay, the other reservoir we have is continental crust. Okay, so this is average continental crust, because continental crust can be divided into two, upper crust and lower crust, right? Upper crust we denote as UCC, and lower continental crust we denote as LCC. Okay, UCC and LCC. Uh, Actually, this is the the average crustal evolution you are given here. But if you want to give the correct or the real evolution, definitely you will see some deviation from this average line also available for what for the upper continental crust, because upper continental crust is more enriched in rubidium. Because upper continental crust, among these two continental crust, upper crust means the upper level of the crust, lower crust means the lower level of the crust. So lower level, at the lower level you have a lot of mafic uh, minerals, mafic rocks, like pyroxenes, a lot of pyroxenes, some olivines also available, and a lot of plagioclase. That such mafic compositions, mafic minerals, do not accompany a lot of rubidium compared to felsic upper continental crust, because upper continental crust is felsic. So a lot of feldspar is there, K feldspar and plagioclase, uh, minerals. So a lot of plagioclase can take huge amount of rubidium. So in that case, look here, when the continental crust is formed, look here, everybody is writing. Yes, here. When the continental crust is formed, if you have a lot of melt crystallization as the upper continental crust, or like granites or something, then you will see slight deviation from this average continental crustal evolution line also, right? So then you can name UCC here, UCC evolution line, and LCC evolution line little down there, an average line can be there, but the lower continental crust will be evolving little depleted like this. Okay, average, lower and average line, and then lower continental crust line and the upper continental crust line. This type of change can also be observed in the isotopic systematics if you analyze the samples, right? So I'm not referring here actually exactly an age, right? you can't say, I mean, we cannot say the time when the upper crust was formed at 2 GA or something. No, that is not like that. Anytime it can happen, right? There are so different time intervals where the upper crust and lower crust was produced, right? Even now is being produced. So therefore, you can't specify any critical time, right? Every time it is happening, right? So it may be present day or it can be ancient, whatever. Okay, so this is how it is happening. But if you just want to show the continuing crustal growth as an average, then you can refer to this black line as the average continental crust. So this is how the Earth's reservoirs are uh, evolving in terms of rubidium strontium systematics. Any question? I'm going slowly because you need to understand. Okay. So if you don't understand, you can ask me. I can explain again. Right. So all these concepts that we have discussed, you have to keep in mind the principles of these isochrons and age equation or generalistic equation. So this is not only for strontium, rubidium strontium. Any present day isotopic system, any initial isotopic composition, and any parent daughter ratio which is available today, and respective lambda to be applied, and you can find out the time, right? If they remain in a closed system, you will come up with an isochron like this, right? Otherwise, you don't get a meaningful isochron. You can get a line, but it might not be the meaningful isochron if this parent-daughter system has uh, exchanged or violated the closed system behavior. Another important thing is there, which I haven't mentioned you yet, that is the temperature condition, right? We have something called closure temperature, right? We are not going to discuss much on that, but remember there is something called closure temperature. Closure. Closure temperature. So this means uh, the maximum temperature a system can afford without breaking its this equilibrium behavior. Okay, although at I mean just making the system open can break the systematics, right? It can violate, it can break. Maybe, for example, if we suppose a closed system, but somehow if some melt has escaped from the system, or if a melt intruded into the system like that, then there can be uh, breaking of the open closed behavior, right? But again, there is a question, why then partial melting, then the melt formed and it escapes from the system. So why don't you consider it as a open or closed system? Yes, it's true, but we are taking the earth or the mantle or the crust as a whole, right? So you have the partial melting here, right? And it produces crust here, but the earth crust system as a whole does not get destroyed any material there, right? So therefore we are considering that scenario. And also, if you are considering just a single rock, if you are considering just a single rock layer, and if you have some evidence of partial melting or something, there may be some areas like this. For example, if you have, maybe if you are looking at a migmatite, right? If you are looking at a migmatite, you can see a lot of leucosomes there, right? A lot of leucosomes you can see. But if you, if you want to do an isotopic analysis for this migmatite, and you are going to take a sample like this, right, from this portion, you look at the sample. Finally, what you are getting, what kind of a sample you are getting now? Maybe you are getting some sample like this, okay, like this, and here you have the melt portion. But you see, most of, majority of the sample will be composed of the melt, right? Your host, or the your other part of the rock, because migmatite is a single rock, but you are having different zones there, right? Leucosomes, melanosomes, like that. But you are not representing this sample very well, right? So therefore, you need to take a representative sample. Whole sample could be crushed, should be crushed in that case. If you are crushing only part like here, you are biased. You are biased only to the melt in this case, because melt is the dominant part here. In that case, just if you want to analyze only the melt, then it's okay. You have to separate the melt like here. And if you want to analyze the rock, the other part separately, then you can take this part. Otherwise, if you want to make the whole rock analysis for this entire rock as a representative analysis, then you have to take the entire rock. So this is again what we think about the closed and open system behavior. This is actually coming with the scale, at which scale you are looking at, whether you are looking at micro scale or mega scale, right? This closed open system thing is coming up, right? Right. So, but for a small scale like here, of course, open. The system is now open here, because you are exposed only to the melt. That means you cannot system. You cannot representatively consider the entire rock which was available before this melting, right? If you want to represent this rock, the composition which was prevailing there before the melting, that is the real rock, right? Because the melt escape, the production is just a secondary product, secondary process due to temperature increase or something, right? So, in order to explain the real rock's evolution, you have to take the original rock. So therefore, this scale is also important, right? So that is again one thing coming in this isotopic systematics uh, about this scale thing. So you can refer one paper written by Elakis in the recent GSSL journal. I think it's in 2020. This has been discussed. This has discussed in very detail with diagrams of production of isochrones, right? Pseudo isochrones, real isochrones, like that, right? Uh, you may not understand everything, but you can have a look. Right. The other thing we were talking about the closure temperature. The closure temperature is the maximum possible temperature that a system can afford without breaking its the close open behavior. So in this case, close open behavior means rubidium strontium closed system behavior, closed open system behavior. Because if the temperature is too high, exceeding this closure temperature, this rubidium, the initial rubidium and the existing rubidium, strontium, they will get all distorted, and some rubidium may be going out from the system, from the mineral or rock or whatever. Then we call this isotopes get reset. That means this initial ratio will be disturbed. Okay, this initial ratio will be disturbed in the continuing system, so that if you just analyze and see this system after the closure temperature, your rock will evolve like that in a different pathway from the isochrone. I mean, not evolution, but it will show a different isochrone after the closure temperature. After the closure temperature, so you can do a test if we have experimental setups, right? We can analyze some rocks, and then we can heat those rocks exceeding the closure temperature, and then you can plot in the same diagram and see the isochrone will be uh, different, right? Because of resetting, we call it resetting of the uh, system, right? It is actually something like you remove your battery from your clock, right? These are clocks. This equation is a clock, right? Because we are measuring the time, right? So if you in your watch or clock, if you remove the battery, what happens? The time stops, right? The time stops, and then if you put a new battery or replace the battery, then it starts again start working, but the time is uh, shifted, right? Unless you make it back by turning around the needles, something like that happens after the closure temperature. So we call the closure temperature is time when the point when the isotopic systematics reset, or we call the resetting the clock of the rock, right? These are clocks of the rock, actually, right? So resetting the clock of the rock is dependent on the closure temperature, right? For rubidium strontium, the closure temperature is not very high, uh, maybe less than 800 degrees Celsius. Uh, Anything in granulite phase is metamorphosed rocks, which are exceedingly higher than 800, might not be suitable for rubidium strontium isotopes systematics uh, in most of the cases, right? It depends actually on the minerals available, right? What minerals you are looking at, because if you take the whole rock, then it might be okay, because not okay actually, but maybe somehow somewhat or okay, because you are considering the whole rock. That means all the effects happen there will be kind of like plus minus. Some effects might be nullified by another effect, something like that. But if you are just taking minerals as for your isochrone, like one mineral, another mineral, plagioclase, biotite, and another mineral, and draw the isochrone, then if the clock has reset in these minerals, then you are not getting the correct isochrone. You will get a different isochrone. So therefore, for mineral isochrone, it's very important, this closure temperature. Of course, for the whole rock isochrones, it's important, but the effect is very severe when you take the mineral isochrones. And also remember, for each mineral, there are different closure temperatures, right? These are experimentally determined, and they can be found in some textbooks, okay, if necessary. So that is there for any isotopic systematics. Closure temperature is very important. So that's why we are much oriented in zircon dating, because zircon has a very high resistance for this resetting. Okay, so therefore that's why people try to use zircon uranium lead system for getting a reliable age, rather than going for rubidium strontium like isotopic systematics. But for low grade rocks or igneous rocks which are not metamorphosed, this rubidium strontium will give you very reliable results, no problem. Because for igneous rocks, it's just crystallization and then cooling, and no metamorphism. So therefore, no heating associated. So therefore, you can apply this systematics for igneous rocks very well. When you go to metamorphic rock, that is rocks, that is the problem, right? Because they are heated during the metamorphism. If it is heated until the granulite phases, then might give you some erroneous results. Okay, so these are the things that we discussed about the rubidium strontium isotopic systematics. And remember compatibility, incompatibility, and when a rock crystallizes, right? Each mineral can have different rubidium strontium ratios. The reason is rubidium will be going to the melt in different proportions, right? You remember the partition coefficient, right? Depending on the partition coefficient, the amount of rubidium and also amount of strontium can be variable in different minerals. Okay, but the whole rock, the entire rock, if you find, that will be equivalent to the original source, because this is the whole rock. This is the whole rock, and we assume since the time of crystallization during this t time interval, there has been no open system behavior. Okay, but although you have different rubidium strontium ratios, uh, they will have different strontium accumulated radiogenic strontium because of this difference in rubidium uh, amounts, right? So therefore, you will have different strontium isotopic values in when you plot them, right? And if they are cogenetic, then you should be able to draw a line. That is what we call the isochrone. So this isochrone represents how these minerals were evolving from the original same initial uh, value, initial ratio, right? So because initial time, different rubidium's were there, rubidium strontium ratios were there in rocks at the time of this crystallization, and then after T time, later, this will go to higher strontium because uh, they have different amounts of rubidium. The more you have rubidium, because rubidium is increasing this way, the more you have rubidium, the more strontium you produce. That's why this is going to the top, and this is moderate. It is going here, and the lowest rubidium will go to the lowest strontium. Right? That is how it is happening. Okay. Right. So you can use this gradient to get the age, and you can get the extrapolation to the y-axis to get the initial ratio, right? Actually, it should come here. And in case if this rock system uh, subjected to another stage of some change, modification, then definitely it should go in a different isochrone line, right? Disturbing this initial ratio. Okay, right. Like we explained the Earth's evolution with different reservoirs here. Okay. So as I said before, there are some complexities. We may want to look into those complexities using these systematics rather than just taking it as a age tool, right? So there can be a lot of magma or lava produced in the earth, and once it comes to the surface, we say lava, but this lava uh, can also be affected by some other processes. But frequently, magma is affected by many processes. Uh, like for example, this situation A here. When a magma chamber is there, a magma chamber is produced when the partial melting brings up some melts. These melts at shallow level because of low pressure uh, produces some kind of tanks, right? It's like a tank, and then from there onwards, they starts to erupt as a volcano, right? Before erupting the volcano, you have a magma chamber. So everything is getting filled into this chamber with time, right? When the time it comes, it's full, right? It starts to uh, explode or erupt as a volcano. Otherwise, it won't be there won't be a volcano in that locality in that place. So in magma chambers, what can happen is they stay there for long time, right? They stay there for long time means like some millions of years, tens of million years, or hundreds of million years, like that, right? During that time, some temperature changes can happen, and because of that, crystals can form, right? Because once cooling is there, fractionation or the fractional crystallization can happen. Some crystals can produce. You can remember the Bowen's reaction series. Uh, some crystals can form there. So what happens when crystals are formed? When crystals are formed, crystal is a solid, right? Still the melt is there remaining. So rubidium prefers melt, as I said, because it is incompatible. So a lot of rubidium will remain in the melt rather than uh, going into the crystal formed. Okay, so a lot of rubidium will be remaining in the existing melt. So the crystals uh, in form in the magma chamber, but rubidium stays mostly in the melt. But it doesn't mean that none of the rubidium goes into the mineral. It goes, but majority will be there. But if you are crystallizing some phase like feldspar, uh, there can be a lot of rubidium going into that, right? But still, the melt will contain a lot of rubidium. So the rubidium will be little by little enriched in the magma chamber because crystallization happening, and crystallization accompanies a lot of uh, I mean less rubidium into the crystal. So therefore, automatically, a lot of rubidium will be there in the system. And another thing, strontium, with respect to strontium, rubidium is more incompatible, as I said. So strontium is like if you are there are two people labeled strontium and rubidium. Whoever the label had as strontium need to go to the crystal because it is less incompatible compared to the rubidium, right? So that also causes depletion of rubidium in the melt because it goes to the mineral, automatically enriching the rubidium composition in the melt. So rubidium enrichment is happening in the melt, right? So finally, because of this rubidium enrichment, with time, if you leave it to stay for a long period of time, what happens? The enriched rubidium will produce a lot of radiogenic strontium. Okay, so with time, what happens? This rubidium enriched melt, it will be showing you very highly enriched strontium composition because a lot of rubidium was there initially, and with time it converted into strontium isotopes. So it will be very high in strontium isotopic composition when the eruption is taking place. So from the magma chamber, finally, when the eruption is taking place, that magma will be enriched in a lot of strontium isotopic composition. So that's why a lot of granites uh, coming from the volcanoes will have a huge strontium isotopic composition, large strontium isotopic compositions. Okay, so that can happen. Such kind of variation or some secondary processes actually. Secondary means it doesn't mean that it's a superficial or near surface process. It's interior anyway, right? But later than the crystallization, so that's why we call it a secondary process. Nothing other than alteration or anything, right? And another possibility is there. The first we discussed under A, and under B we can discuss another scenario. That is, when this magma chamber is there, there is long-term magma stagnation within the crust, right? What can happen? This magma can react with the host rock, the host crustal rock, right? So there can be interactions in between. So the crustal minerals can be dissolved, and also at the same time, some new minerals from the melt can be crystallized, right? So actually, this is called AFC processes. We call it AFC. What is AFC? Anybody knows? Those who do igneous petrology will learn about this AFC. Assimilation and fractional crystallization, right? Assimilation is melt rock reactions. During that reactions, you have the fractional crystallization happening. In the scenario A, you had just the fractional crystallization only, no reaction, anything. But here, you have the reaction between the host rock, and then you have the assimilation as well. Assimilation means a kind of reaction, right? So in that case, there will be exchange again, and if the crust, because the crust is always rich in rubidium because it is incompatible, already formed crust will have a lot of rubidium, and therefore uh, again high strontium bearing, strontium isotopic bearing material will be their involvement, right? So like that, there can be high strontium rich magma coming out again from the magma chamber. Okay, that is the second scenario, that is second possibility. And the third one, what you can do here is number C. There are possibilities for in the magma chamber. They are uh, they are mixing together before the eruption. Okay, before eruption, one magma chamber can be joined with another magma chamber, because sequence of melts coming from the mantle, and batches of different batches of melt, while one is residing in the shallow crust as one magma chamber, another melt can come up and come into that, and that will produce another magma chamber and mix together, right? So this mixing of magma can happen, right? So this mixed magma will erupt as a very different composition, right? So it can be either depleted strontium or enriched strontium. We don't know. It depends on what type of magma coming. For example, if a magma came all of a sudden from a lower mantle, like here, look here, look. If something is coming from the lower mantle, right, like here, plume-like thing, and then mix with this magma in the shallow magma chamber here, right? What can happen? This magma is depleted in strontium. Remember, lower mantle is depleted in strontium, right? So once you have depleted strontium coming into the enriched magma chamber, what happens? Everything goes down, right? The average composition goes down, right? Then the erupting magma will be having a depleted strontium isotopic composition, right? But if an enriched magma chamber, magma melt came to mix with an existing magma chamber, there is possibility for increasing the strontium isotopic systematics. So like that, such changes can happen. So to trace this type of effects, we can use strontium isotopic systematics, although we are not interested in determining the age in this type of cases. Right? Actually, age determination is not reasonable here. Why? Because this magma is already mixed together or reacted or whatever, some process has happened, right? So that means their open system behavior may have exhibited, right? Therefore, but the case A is okay because there is no open system. I mean, nothing came in from the outside, from the exterior. But other two cases, you cannot find a reasonable isochrone because they have been affected. The open system behavior has been broken. Okay, did you understand? Okay, right. So this is how the rubidium strontium isotopes behave. Actually, this process is not only common for the rubidium strontium isotopic systematics. It can be valid for any isotopic systematic, right? Mixing and all can change their existing compositions. I think you got these points well, right? Okay, let me show you some seawater isotopic compositions of strontium with time in the seawater also, like in the normal rock or the crust, isotopes change, vary the composition, right? So there are several controls on seawater isotopic composition, especially strontium isotopic composition. Strontium flux rate, right? Strontium flux rate. That means how much strontium you are getting into the system, into the water, seawater. Okay, whether the flux of uh, strontium is what, rapid or not. Okay, if a lot of erosion is taking place, you can realize a lot of materials from the continents will come into the uh, sea, right? So there is a flux, strontium flux. And also the initial strontium ratio existed in the seawater. Whatever the initial ratio existed at the time of that seawater formation will affect whether it will be evolving highly or uh, not that high value. Okay. So the runoff brings a lot of rubidium into the seawater, also strontium, so that you will finally change the rubidium strontium ratio in the seawater, right? Crustal erosion and runoff of materials from continents. Okay, this is continents. This is continent, and this is sea. So it will change the seawater composition. But the oceans are very big, very large. So all these isotopic systematics will, I mean, strontium isotopes will get homogenized with time, little by little. Like, I mean, still it might not affect severely to the average seawater isotopic composition, but maybe at the extreme edges, like here, you will see some drastic change. But when it comes to the average composition, gradually it will be homogenized to a value like this. Okay. And because river flux always have high isotopic composition, because river flux, you have a lot of sediments, right? Lot of sediments, they are taken here. The sediments are coming from crustal rocks. Crustal rocks contain high strontium values, so therefore their isotopic composition is high always. But when it comes to the ocean, with time, they will get diluted. They will get diluted, and the average seawater isotopic composition will be there, evolving into this type of a value. Okay, it's again, it's a mixing like process, like in the magma chamber. And another possibility is uh, you have the hydrothermal exchanges. Hydrothermal exchanges. What is this hydrothermal exchanges? Hydrothermal solutions can bring up uh, strontium, rubidium, various amounts, right? They can bring, but their isotopic composition is lower than the riverine input. Why? This hydrothermal exchange is coming from the mantle sections, right? So in the like mid-ocean ridges mainly, right? So mantle isotopic, strontium isotopic composition is lower than the crustal isotopic composition, right? You learned it before. Therefore, they will bring up low strontium ratios, but still with average with circulation, with time, it will come up to a average value. And also carbonate crystallization, right? Carbonate crystallization. So carbonate crystallization happens in the sea. How that can happen? The animals or creatures available in the sea, when they die, what happens? Their shells get dissolved, and those carbonates will add strontium, right? But those carbonates you see here, the strontium isotope ratio is like 0.709. It's almost equal to the average seawater strontium isotopic composition. Why is that? Because those creatures or the animals, they lived in the seawater, so they were in equilibrium with the seawater, right? So almost same isotopic composition, but maybe some variation is there anyway. But still that will add to the seawater, but which will not turn the seawater into drastic change, because almost similar composition. So therefore, strontium flux rate is important from different sources. So carbonate crystallization, hydrothermal exchange, runout, or riverine input, whatever, this will change isotopic composition in the seawater. So you can see this seawater strontium isotopic curve, which has been measured from old and young carbonates, uh, giving a variation like this. You can see a curve, right? Some fluctuation like that, right? Some curve is there with time. So you have the time here. This is present day. This is present day, and this is 500 somewhere. So this is very close to our metamorphism time, right? 550, right? So what has happened during these times? So you should know that these global tectonic processes have caused seawater isotopic composition variation fluctuations. So that's why you have a some variation like this, some downs, some highs like that. Okay. So you should be able to find out each and every event related to these fluctuation. For example, these troughs, right? So these troughs could be related with some events, right? And these tops, right? These high plateaus could also be related to, sorry, related to some events. Okay. So these fluctuations are a result of some kind of activities. Broadly, they can be related with mountain building processes and hydrothermal activities. Okay, mountain building processes and hydrothermal activities, or you can write another thing uh, as rifting processes, as rifts, right? You know rifts, right? Rifts means continental breakups, okay? Extension. Mountain building is always associated with compression. Compression means collision of plates, right? Breaking of plates, like fracturing of plates, are extensional activities or rift activities. At the same, also hydrothermal activities can cause depletion of seawater isotopic composition, whereas mountain buildings can cause increase of isotopic composition. in the seawater. Why? To increase the isotopic composition of the seawater, you saw this strontium flux rates, right? They are associated, and you see here riverine input is giving you high values of strontium. Why? Riverine input means it carries a lot of sediments. So why a lot of sediments are in the sea, in the rivers? What kind of situations? When there is heavy erosion, okay? When there is heavy erosion, you can see like Nestomalt, the river water, lot of sediments that carries lot of broken materials, sediments, minerals, everything. Okay, so to make erosion high, what do you need? If you go to Goal and another person goes to Nuerelia and check the erosion rates, how do you see? Nuerelia will have lot of erosions, right? But gold, the lowlands will have less erosion. What is the reason? Availability of mountains, right? Availability of mountains. So if you have mountains, that means higher elevations areas, you will have a lot of erosion. So remember, during the Earth's evolution, mountain building times records the highest times of erosion, highest uh, erosion erosion rates, right? Durations. So in the case of mountain building, that's why you see a lot of strontium isotopic composition increasing in the seawater, right? So you can see Gondwana orogenesis here at about 500 MA, 550 or 500 around that time. You see strontium isotope composition has increased. And around 400 also there has been some uh, some increase, because during this 400 500 a lot of mountain building events have taken place, you know. Pan-African orogeny, Kunga orogeny, you remember in your third years you should have learnt them, right? Kunga orogeny is around 400 to 450, and this Pan-African or Mozambique belt formation, it's around 500 550, right? And various other events later on in the Pangea supercontinent. A lot of collisions, a lot of events related with that has caused sea water isotopic composition increasing at different time intervals. Okay, and 200 million years, around 200 million years time also there has been some global strontium isotopic change in the seawater, right? Like that, there has been different events uh, here. Now, the present day, the today, seawater is getting more and more isotopic compositions of strontium. Why? Because of Himalayan uplift. Although there is no plate collision, I mean, there is plate collision, but not like in the Gondwana, I mean, but still this Himalayan, Eurasian and Asian plates have, the Indian plates have goes to the maximum compression, but still little by little upliftment is taking place, right? So upliftment means you are increasing the elevation, increasing the mountains. So gradually the erosions I mean the sediments coming out from there as a result of erosion will also has also increased during the recent past. Okay, maybe last 50 million years or so, from here to here you can see seawater isotopic composition increasing like this, a trend, increasing trend because of this Himalayan uplift. Likewise, these mountain building or high erosion causing rate activities have caused these uh, strontium isotopic composition in the seawater to increase, to fluctuate actually, right? Increase and decrease, increase and decrease. Decreasing is related with another thing, but increasing is related with this mountain building or uh, high erosions. So this decreasing has happened also, as you can see, in time to time, placed, and also alternatively, right? Once you have an increase, there is a decrease. Increase, decrease, increase, decrease. Why this happens? So this increase happens due to orogenesis, right? Orogenes, different orogenes. That means collisions of continents. Okay, one continent collides with another and make a mountain. Okay, so after this collision, after some time, what happens? This will start extension. This will start extensions. Okay, because once collided, it can't be there as it is in the equilibrium condition. The two collided continents tries to go back to their original positions, right? Bounce back, like you hit with a rubber ball to a wall, it comes back, right? Something like that. It tries to do that, but it is very difficult. But only thing what happens is just making a fracture. It stops by a sequence of fractures, forming fractures. So once you have fractures formed in crustal level, what happens? The the interior mantle melts, or hydrothermal melts, or whatever can come up through those fractures, and finally they can come into the sea from the ocean floors. Okay, but the mantle isotopic composition of strontium is lower compared to the crustal composition, and also hydrothermal composition you saw here has low value. Therefore, average isotopic composition of the seawater will drop. So that's why this type of rifting events depletes the uh, seawater isotopic composition. Okay, so you can see seawater strontium isotopic composition is depleting due to hydrothermal or rifting activities, right? So that's why I put rifting also there, right? Hydrothermal or rifting activities. So always collision is followed by rifting. So therefore, increased isotopic composition, and then another episode of decreasing isotopic composition, and again increasing isotopic composition. Likewise, alternative uh, change can be there. Okay, so this is what happens throughout the time during the Earth's evolution, so that you encounter in the long term average seawater composition almost no change, but time to time it has changed. Okay, but if you take this as an average, as a global average, your the present day isotopic composition in the seawater is something like here, right? Because of this Himalayan thing, a huge uh, change has happened here from the previous isotopic composition. For example, about 100 million years ago, the seawater isotopic composition was somewhere here. Average seawater isotopic composition was somewhere here, but now it's here, but still it remains as it is. The reason is uh, the oceans are large compared to the continents. Therefore, even though you add a little amount of uh, strontium into the sea, it won't change drastically unless you provide a huge amount of strontium input uh, from a mountain building process like this. Okay, it's like you add some salt to water, right? If you add a very little amount of salt, you don't feel the saltiness there, right? So salinity uh, change also. Even you see the salinity also has a constant composition. I mean, almost constant in the seawater, right? There are a lot of salts coming from the continents, right? But still salinity is not drastically changing. But given specific times, maybe salinity has changed like this. Someone has to look into that. Maybe already they are, so you can check that also. Okay, so this is how the seawater isotopic strontium isotopic change throughout the time. Much of the people, I mean, many of people have an interest to study strontium isotopic composition in the seawater. because there are a lot of activities there, like carbonates, fossils, shells, and then hydrothermal activities, like that. These activities are, it can be reflected very well by strontium rather than other isotopic systematics, because strontium variation can be reflected easily with these changes. That's why people look at a lot of strontium isotopic compositions in seawater rather than neodymium or other isotopic systems. So these isotopic compositions are determined. So because at 400 million years ago, do we have seawater here with us? To measure, to find out what it is? No, we don't have, right? But how can you measure them? Assuming that is the same isotopic composition as the seawater, you can use the old and young carbonates, right? Old carbonates to here, young carbonates to here, right? But here we have the present seawater, so we can measure directly. But for other times, you have to find out fossils and determine the times, different time intervals according to fossils. Then you can find out their composition. And you see here, carbonate crystallization is giving you almost same as seawater isotopic composition, right? This is present day. So that means carbonates were in equilibrium with seawater. So we can assume in the past also the carbonates were in equilibrium with the seawater, right? So therefore, the isotopic composition you get from a carbonate or the fossil, or the shell of a dead creature should be equal to the seawater isotopic composition. So that is how this curve is generated, right? So some fossils or some shells lived in this time, for example, have shown low strontium isotopic composition. And some fossils which have ages like this, 500, have shown high strontium isotopic composition. So likewise, people have mapped it and then plotted various with respect to various times. So then you have a automatically you are ending up with a curve. Okay. And why you don't have the compositions before these ages, like say 1,000 million years, 2,000 million years, 4.5 billion years, like that? Why don't we have? Hmm? What's the reason? Can you tell me? Anyone? Those you have the mic with you now. I want to check the mic also. So you have to speak. Somebody has to speak. Who has the access to the mic now? So unlucky. So tell me the answer for my question. Why you don't have seawater compositions values beyond say yeah, maximum like 550 we have, right? From there above, maybe very rare, only few you have. Why they haven't plotted them into this curve? Give me an answer quickly. It's not geology. Where is the mic? So you are passing the mic now. Somebody has to tell. It doesn't matter who has the mic or not. Someone has to tell. Someone has to give an answer. You can discuss all and give one answer. නිදිමත යන්නත් එක්ක ආන්සර් එක දෙන්න දැන් ටක් ගාලා. තා පොඩ්ඩයි වෙලාව තියෙන්නේ. Yes, another 1 minute I can give you. You can discuss and give the answer. Yes. Okay, time up. Someone has to tell whatever you discussed. Where's the answer? I don't hear anything. Yes. Quickly, quickly. Don't waste the time. So you will get minus marks for your. Everybody will get minus marks then. I will reduce the marks. I gave you the opportunity to discuss, and now it's a matter of presenting only. Whatever you discussed, you tell me. I didn't hear anything. Yes.
The carbonate deposits are formed as and destroyed or started to form at a major tectonic event or on the latest that by 500 or 600 million years ago was survived after a tectonic event as ice age or some.
So that means we don't have like tectonic, we didn't have any tectonic event before. Does it mean? Or
Only the preserved ones are survived after a major tectonic event like
yeah, you mean only we have the preserved carbonates like 500 million years or younger? Is it? The previous carbonates, I mean, previous carbonates preserved are not available now, like that?
yes. Or first we crystallized by the tectonic events.
Destroyed by the tectonic events. Later tectonic events have destroyed the old carbonates. You mean? Okay. Okay. You have to think about it. How many of you are there? The biology stream. Because this is not geology. This question is not geology actually. Hmm? How many of you are there in this group? How many of you? Just raise your hands, biology people. Oh, the majority. Only one maths. Oh, really? Then you should have known the exact answer. When did the life started? I mean, the carbonate shells started in the earth. To have Precambrian life, I mean, Archean life, Archean brachiopods, or uh, whatever the shells that you can find in an ocean. Have you ever found any fossil as old as Proterozoic or Archean? කවද්ද ලයිෆ් එක පටන් ගත්තේ? ලෝකේ ෂෙල්ස් තිබුණාද මේ ආකියන් කාලේ? ඔය මේ ට්‍රයිලෝබයිට්ස්ලා එහෙම ඉඳලා තියෙනවද ඒ කාලේ? එහෙනම් කොහොමද මේ අයිසෝටොපික් කම්ප්‍රෙෂන් එක හොයන්නේ? ෂෙල්ස් වලින් නේද හොයනවා කියලා කිව්වේ. හ්ම්. එතකොට ෂෙල්ස් තියෙන්නේ අවුරුදු 30යි නම් අවුරුදු 30න් එහාට අපිට ඒජ් එකක් මේ ඒගොල්ලන්ගේ ප්‍රොපර්ටි එකක් ගැන කියන්න බෑනේ නේද? So you have to think of the age, right? So that is the answer there, right? You have the answer there when whenever the fossils, oh sorry, I mean these shells, these sea shells started to appear in the planet. Okay, that's why we don't have a continuous curve. We can't trace that anyway, right? But seas were there before 500 even. Because in the Rodinia supercontinent, there has been some kind of ocean formation, ocean closure, right? Likewise, we don't see any evidence for preservation of the fossils or for preservation of these seashells. As you said, in one hand, it can be also because we don't know about any life sign as old as the Earth's earliest history. But mainly, I was asking why we don't see in this graph ages before 600, right? The simple answer should be because we don't have shells there older than that age. Okay, right. So we will stop here for today. Then we will continue next week and make sure you sign the attendance. Next time we will start a new isotopic system. We have to complete several isotopic systems, samarium, neodymium, lead, uranium lead, thorium lead. How many weeks are left? How many classes are left for this semester? කීයක් තව ඉතුරු වෙලා තියෙනවද? How many classes are left?